So you've done it. You've come up with an incredible breakthrough in high-strength aluminum. It's a total game changer, right? Something that could completely shake up aerospace and automotive. But here's the big question. How do you actually protect that idea? Well, that's exactly what we're going to get into. We're going to dive deep into the world of aluminum welding patents, not just to see how these amazing ideas come to life, but to figure out how they're strategically locked down.
You know, there's this weird paradox right at the core of modern engineering. We've got these amazing materials, these aluminum alloys like the 7000 series, and they're just unbelievably strong and light. But they have this one huge, fatal flaw. The moment you try to weld them together the old-fashioned way, they just crack.
So why? Why do our strongest, lightest metals just break apart when we try to build with them? I mean, this is the multi-billion-dollar question, right? It's the thing that engineers and metallurgists have been banging their heads against for decades. It's a huge roadblock that limits how we build everything from jets to supercars. And let me tell you, solving this puzzle, well, that's not just a cool engineering win. It's an absolute intellectual property goldmine.
All right, so here's the plan for today. First, we're going to dig into the science of why these alloys fail in the first place. Then, we'll check out some of the brilliant fixes engineers have come up with. After that, we're switching gears to strategy, how you build a fortress around your idea. We'll even tear apart a real patent to see how an examiner thinks. And finally, we'll peek over the horizon at what's coming next. Let's get into it. All right, first up, the unweldable alloy problem. We've got to get into the metallurgy here, because you can't really get the solution until you understand the problem, right? It all comes down to the physics of how metal cools. And trust me, that's where the massive headache begins. So what's actually happening here? Picture this. You've got this molten pool of weld metal, and it starts to cool down and solidify. As it does, these little solid grains start to form. The problem is, the last little bits of liquid metal get trapped between them. Now, as the whole thing shrinks, it's pulling those new grains apart. If that trapped liquid can't rush in to fill the gap, boom, you get a crack. This is what's called solidification cracking, or hot cracking, and it's what makes these amazing high-strength alloys like 7075 just a nightmare to work with.
But of course, for an engineer, a problem like this is just a challenge waiting to be solved, and the solutions that have popped up are seriously clever. They basically follow two completely different paths, so let's check them out.
So, you've got two main choices. Path number one, rethink the process. Find a way to join the metal without actually melting it. Path number two, reinvent the material. Design a filler wire with a special chemistry that just stops cracks from ever forming. And you know what? Both of these paths have led to some huge patented breakthroughs. Okay, let's look at the process side first. This is where you get something like friction stir welding, or FSW. This was a totally radical idea patented by the Welding Institute way back in '91. Instead of melting the metal, you take this rotating tool and you just smush the two pieces together. It plasticizes the metal, think of it like stirring really hard butter, and forges them into one piece. And the genius part? No melting means no solidification cracking. Problem solved. Just like that. Now for that second path, reinventing the material. And this is a perfect example. On the left, that's what happens when you try to weld 7075 aluminum with a conventional wire. See that big crack? Yeah, not good. But on the right, that's a weld made with a special filler wire that's been beefed up with nanoparticles. So what are those little particles doing? Well, they act like tiny seeds, giving new crystal grains a place to start growing. This creates this really fine, interlocking grain structure that's just way more resistant to cracking. Pretty smart, huh? Okay, so you've cracked the code. You've solved the cracking problem. Maybe you've got a revolutionary new process, or maybe it's a brand new material. Awesome. So, now what? This is where we make that huge pivot from the lab bench to the boardroom. How do you turn that brilliant discovery into a protected, valuable asset?
There's a really great way to think about this that comes from the FEC group. They talk about IP as being both defense and offense. Think of it like this. Risk minimization, that's your shield. You patent your core technology to protect your business and stop competitors from just ripping off your hard work. But then you have chance maximization. That's your sword. You use IP analysis to scout out the landscape, find new business opportunities, and go on the attack.
And what this really shows is that a strong patent strategy doesn't just happen on its own. It's not just about what you're doing, you have to look at the whole picture. This IP5C framework is a great way to do that. It forces you to look at your own company, your customers, your competitors, yeah, but also your collaborators and even your suppliers. You have to understand the IP of the entire ecosystem. That's how you carve out your own unique, protectable little corner of the world. All right, now for the really fun part. We're going to put on our patent examiner hats. Let's actually tear down a real, recently granted patent and see what makes it tick. What makes an application strong enough to get that stamp of approval?
So for our case study, we're looking at a company called Prysmian. They just got a patent for a new aluminum welding alloy, which is a perfect example of that reinvent the material path we talked about. So let's dig in. What exactly did they claim, and more importantly, how did they convince an examiner it was a real honest-to-goodness invention? Okay, first thing you notice, the incredible specificity. Prysmian didn't just walk in and say, hey, we made a better alloy. No way. They laid out a super specific recipe. It's a 5000 series base with these exact amounts of magnesium, zinc, silicon, and copper, plus these special additives. And get this, look at the exclusion. They say it's notably free of zirconium. Now, why do that? Because by excluding something that's common in other alloys, they make their claim incredibly narrow and precise. It makes it way harder for anyone to say, oh, that's obvious, or that already exists. It's like they're creating a unique, defensible chemical fingerprint. Second point, they didn't just describe what was in it, they described what it does with a hard number. The patent claims a welding efficiency of 82% or higher. Now, if you're a patent examiner, that's music to your ears. It's not some vague promise like it's better or stronger. It's a number. It's quantifiable. It's testable. It's a clear, defensible line in the sand that separates their invention from everything that came before it.
And third, and this is so important, they brought the receipts. They showed their work. Look at this data. It shows a huge reduction in crack length compared to other alloys. You can't just file a patent with a good idea. You need cold, hard evidence. An examiner needs to see solid comparative data that proves your invention actually works. This is the kind of stuff that turns a neat idea into a validated, defensible solution.
So, what's the big takeaway here? A strong patent is way more than just a clever idea. You need three things. You need to be super specific in what you're claiming. You need hard numbers, quantifiable metrics that show it's better. And you need the data to back it all up. That's what proves you've made a real inventive step. That's the magic phrase. It means your idea is not only new, but it's not obvious to an expert in the field. You nail those three things, and that's how you get your patent granted.
Okay, so let's shift our gaze to the future. I mean, the world of material science and welding is moving at lightning speed. So where are the next big intellectual property battles going to be fought? What's on the horizon?
Well, it looks like there are three big frontiers opening up. First, you've got AI and simulation. People are patenting the process of using computer models to design perfect welds before they even strike an arc. Second, we're seeing totally novel alloys being developed. Think aluminum scandium, that are made specifically for things like additive manufacturing and laser welding. And third, it's all about global strategy, using frameworks like the Patent Cooperation Treaty, or PCT, to get your patent protected in a whole bunch of countries all at once, efficiently.
And hey, this isn't some far-off sci-fi stuff. This is happening right now. Take Scandium Canada. They just filed one of those PCT applications to protect a new aluminum scandium alloy designed specifically so it won't crack during 3D printing. They're already making moves on this new global chessboard.
And that brings us right back to where we started. It doesn't matter if your innovation is a new material, a clever process, or a smart algorithm. The rules of the game are the same. Be specific, use hard numbers, and build a strategy that not only defends your turf, but also opens up new opportunities. The next great idea is definitely out there. So the real question is, how are you going to protect it?